Exactly the same as a between or independent measures ANOVA. If we find a significant ANOVA, we are not done. We have simply been given license to now ask the question, where is the differences? Now, again, we do know that if it is a significant difference, that at least the highest mean group is significantly different from the lowest mean group. What we don't know is any of the additional groups. Now, in this case, we're almost always going to use Tukey's HSD as it works best when there's a near equal sample size, and as the repeated measures of within subjects ANOVA has an equal sample size, that's usually what we're going to be using. It basically is computed the same way as the within subjects or the between subjects ANOVA, except that the MS within is replaced with MS error. So again, Tukey's HSD is Q, a calculated number that we'll get to in a minute, with the MS of error divided by small n, the number of participants in any one group, and again, we're going to take the square root of that. So Tukey can always be used for repeated measures since you should always have equal sample size for each group in the repeated measures test, because either they are the same people or they're people that have been matched, which means, again, they should be an equal number in each condition. So again, to get that Q value, we're going to look at the number of treatments. And again, this is not degrees of freedom between at the top. It is simply K, number of groups, divided by the degrees of freedom error, which is the degrees of freedom from the bottom of the condition. In this case, K minus 1 times N minus 1. And in this case, we're going to have a 3 by 10. We're going to see that our Q in this case is 3.88. And again, that Q is based on the idea that we're looking for significance values at 0.05. So we're simply going to now calculate that Q. So we have the Q of 3.88, we had our mean squares of error of 1.52, and we have our small n of 6. So we're simply going to run through that equation and find out that our HSD is 1.94. So if we look at the means of what the sample is that we've been looking at, the baseline mean for baseline to spring, the baseline score was 2.0, the spring score is 3.13. That's a difference of 1.33, which is a smaller difference than the 1.94 we have to find for us to claim significance. There is no significant difference between coffee consumption between baseline and spring. We now want to look at the difference between baseline and summer, our high and our low score, 2.0 at baseline, 4.83 at summer. We again get the difference between the two, 2.83, and again, this is an absolute value, and that is larger than 1.94. That is a significant difference. And finally, we can look at the difference between spring and summer, 3.33 and 4.83, a difference of 1.50, again, too small to be significant. The only significant difference in this data set is from baseline to summer, the start to the end, the highest score versus the lowest score. The medium score is statistically not differing from either the lowest or the highest score. So coffee consumption does significantly increase from baseline to summer, but that is the only significant difference that we found. Now let's briefly talk about matching. We use matching to reduce error for a between subject design by using a repeated measures design if it is theoretically and methodologically sound that we actually can match. And when I say theoretically, that means that you've done a thorough literature review about particular individual differences that might impact your DV. Whatever your outcome is, if we're claiming there's no individual difference, we need to do some research. What are the individual differences that may cause an impact on that outcome? So if, for example, if you're looking at depression, and previous research has shown that social economic status is related to depression, gender may be related to depression, sexual orientation may have some relation to depression. If those are factors, we need to make sure that we match on all of them, that there's an equal number of men and women in every condition, that there's an equal representation of social economic status across each one of our conditions, and maybe an equal number of various sexual orientations across each condition. In fact, ideally, we would want, for example, a straight female low SES in all three conditions. We would want a straight female high SES in all three conditions. We would want a gay female low SES. You start to see the difficulty with matching. To truly do matching, even on just three factors, becomes fairly complex. And again, is that the only three individual differences that may impact depression rates? Age may very likely, in fact, impact depression rates. So when you're choosing a matching design, the first thing you need to do is theoretically ask what individual differences could occur that may result in differences in my outcome, my DV. Once we've actually figured that out, we then need to figure out how we're going to match. And we can match on various techniques, and we're going to talk about this more in upcoming lectures and including next semester. But generally speaking, what we usually think of as matching is what's called exact matching. Once we've picked out all of the variables we want to match at, we want to measure each individual on all those attributes, and then we want to find exact matches. Now, we can try to do various techniques of statistically aggregating. In other words, we combine those various attributes into a regression score, and then we try to find people with the same regression score to match. But no matter what, the matched pairs or groups are therefore treated as single subjects. They're treated as the same person. So again, our straight female low SES, Sally, is considered to be the same person as our straight female low SES, Jane, in condition 2. And once we've actually done this matching, if we can defend it, if we feel confident in it, we can run the within subjects ANOVA to do our hypothesis testing. So for example, here's a quick, very simple example of a matching. Basically, we decide that the one thing that might actually have a relationship to coffee consumption is how attentive the person is. So we measure attentiveness first, and we look for people that have the same score. And once we have that, we then measure their coffee consumption, the outcome, and match them as if they're repeated measures. So for example, Ingrid and MH both have an attentive score of 4, so they are going to be considered to be the same person for the purposes of a repeated measures design. Now again, notice this is exact matching. What if I have someone with an attentive score of 3 and no one else has a 3? Well, if we're doing exact matching, that participant is not going to be used for this study. I don't have someone to match them to. So we could also end up losing participants. And again, as you get to more and more variables you're matching on, you get into more and more likelihood that you're going to lose data through this process as well. So you can do this. There are some practical applied situations where this is something that may be worth doing, especially if you're trying to look at a fairly small effect size and you do not have the ability to use the same people in each condition. It may be pre-existing data, but you have a lot of actual information about individual differences that you can use for matching to allow you to really fine-tune your study. Just recognize that you're always going to have to theoretically and methodologically defend the matching that you've done. Because by doing matching, you're getting to use a statistical technique that assumes identical people are in each of those conditions. So just some quick wrap up on the assumptions of the ANOVA. The outcomes should be normally distributed within each group. So not only should the outcome, which needs to be a continuous variable, need to be normally distributed across the groups, it also needs to be normally distributed within each group. The variance between the groups should be homogeneous. In other words, we shouldn't be seeing different variance from condition to condition. Not only should it be normally distributed, it should also look fairly similar. And again, the observation between the participants should be independent if it's an independent design or between subject design. So recapping, independent measures ANOVA, we have access to a larger sample size, may or may not be able to test or retest over time, or we're simply worried about the potential of maturation and carry effects. And again, we're going to have to estimate the individual difference on the top and the bottom of the equation. With a repeated measures design, the number of available subjects may be limited. We may be trying to make overtime comparisons. We may actually be trying to reduce error because we're looking for a smaller effect by reducing that individual differences. And again, we have to recognize that now we have the potential for carryover effects. So again, just kind of keep in your mind why we use these two techniques, why they're mathematically different, and how they can be used to basically answer different questions, but also could be used to answer the same questions depending on what you're wanting to focus on and what you're wanting to try to achieve.